In this lecture, we'll discuss the design of cache memory, which is the most important component in the design of a memory hierarchy for a processor. So a cache memory is a level of the memory hierarchy that is closer to the CPU than the DRAM memory. When we talk about the organization of a cache memory, we need to talk about the concept of a cache block. A cache block contains multiple words, and the cache block is the unit of transfer between the cache memory and the lower level of the hierarchy. The lower level of the hierarchy may be the main memory or may be another level of cache memory. Most of the current processor architectures have multiple levels of cache. We refer to them as L1, L2, L3, and some of the current processors have a level L4. So the size of the block in each one of the levels may be different. So I could, for example, have a block size at the L1 level, which is different than the block size at the L2 level. The block size is the minimal amount of data that gets transferred between, for example, L1 and the level below L1. For example, I could have a cache with 4 word blocks. In that case, if each one of those rectangles represent a word, this would be a block of data in my cache. So if I have a cache that has a 4-word block like this, and each cache has multiple such blocks, so I could have, for example, a cache that has 4K 4-word blocks, where 4K is 4096. So in that case, what I would have is something like this, where I have the first block, the second block, and so on. I think the video is not showing the division of the blocks over here, but there is a division in these slides when you check these slides later. So each one of those lines has 4 blocks. Actually, the video seems to be showing this first block as 2 blocks. So if we have these 4 blocks in each line, we want now to give a unique identifier to each block. So how many bits do we need for each of the identifiers that we have? So if I have 4K blocks, I need to be able to have 4K, that is 4096 different identifiers. So the number of bits that I need to produce 4096 different numbers are 12 bits. Why do I know it's 12 bits? Because 2 to the 10 is 1K, 2 to the 10 is 1024, and 2 to the 2 is 4. So I have 4 times 1K, so I have 2 to the 2 times 2 to the 10, which makes it 12 bits. So the first, the identifier that I will give to the first block of 4 words will be the identifier 0000. The second one will be 00001, all the way to the last one that will be all ones. So I simply number the blocks from 0 to the maximum, and what I need to know is how many bits do I need to identify each one of those blocks. The unique identification of each one of those cache entries or each one of those cache blocks is the index of that block or the index of that entry. How do we find a word inside the block? Well, now that I can identify a given block, I need to measure the distance in bytes from the beginning of the block to that word. Given that I have 4 words in the block, I have the word at 0, at 4, at 8, and at 12. If the position of the word within a block is the word offset, because I have 4 words, I will need 2 bits to identify the word in the offset. So the slide asks, how many bits do I need for the offset? Well, I'm gonna need 2 bits to identify the word, and there are 2 bytes inside the word. So I have 4 bits to identify which word. So the word 0, word 4, word 8, and word 12. So the total offset will be 4 bits, and those 4 bits could be divided in groups of 2. The lower 2 bits could be called the byte offset, says which byte inside the word I want to access. And the upper 2 bits can be called the word offset, that is which word position I am at. Now I want to find a word in this cache. So for example, if the processor makes an access at the address 0xFF000028, how do I find that word? So the processor is saying, I would like, for example, to load the word from this address. How do I find that word into the cache? What I'm going to do, I will take the 32 bits of that address, and I will divide those 32 bits in 3 separate parts. I'm going to reserve on the right-hand side in the least significant bits the offset. Those were 4 bits. And then I will take the next 12 bits, that are the number of bits that I need to get a unique identifier for a block, to find out which block inside the cache I'm accessing. So that tells me that I am accessing that block, and I take the lower 4 bits to find which word, and that tells me that this is the word that I am accessing in this example. Now the processor decides to do a different access, and this different access is to the address 0x80010028. So I'm going to do the same process. I'm going to reserve the last 4 bits, and I'm going to take the 12 bits that correspond to the index, and I'm going to use the index to find which is the block inside the cache that I'm accessing, and that will tell me that I'm accessing that word. So the question now is, how do we know if the word that's in the cache is from the address at 0xF000028 or from the address 0x80018028? Both of those would be exactly in the same place in the cache, as we could see when we decompose the address into the index to find the position, the block into the cache, and the word offset. The answer is that in order to know what is the block that I actually have in the cache, I need to store the rest of the address that I did not use to find it in the cache. And the rest of the address will give a name to it. It will be the tag. And so I'll store that in front of the block. So that's additional data that I'm going to store in my cache, so that I know which block is stored in that position of the cache. So I'm going to have one such tag for each one of the blocks. So this is a portion of the address that I store along with each cache block to identify which address is the memory, in the memory the block came from. That portion of the address that I store in the cache is called the tag. So I tag each one of the blocks in my cache with the memory address that the block came from. But I don't need to store the entire memory address. I only need to store the bits that I did not use for the offset or for the index. So my tag in this case for this access will be the 0x8001. So this is what I call the tag, and what I have to the right are the blocks. So how do we know now that the cache has a valid block for the requested address? So I will have an additional bit that tells me whether the data that's stored in that block is valid. Because, for example, when I just turn on my computer, the data in every block in the cache will be invalid. So as I bring data to the cache, I will be flipping the valid bit for each one of the corresponding blocks to be valid. So this is my valid bit, that's my tag. So now I have a valid bit that's associated with each cache block, and that indicates if the content in the block is valid. So in this design, there is only one place in the cache for each memory address, because Once I am giving an address such as 0xFF0028, as I do the decomposition, there is only one place in the cache that word can be, and is in that position. And if I'm giving this address, there is again only one place that it can be, and it will be in that position. So as we can see, there will be many such addresses that will be in the same position in the cache. But because there is a unique mapping between a memory address and the position in the cache, we say that this is the mapping between the memory addresses and the cache blocks is a direct mapping, because there is a one-to-one mapping. The problem is that with this mapping is that there are often conflicts into the cache for competing memory addresses. So I may have a piece of code in my program that is fairly small, but will constantly be missing in the cache because I have two accesses that are writing on top of each other, and both of them can go only to one specific position in the cache. I like to avoid such conflicts. Those are called conflicts into the cache, and for that I need to improve the design. But before we improve the design, let's look at this different representation of how we do the access for this direct mapped cache. So we can divide the access into, in this case, the author is calling this a byte offset, because it's assuming in this specific case, it's assuming that each block has a single word in this drawing. So in that case, with a single word, and there is 1024 words in this cache, so each word is 4 bytes, so this is a 4 kilobyte cache. The size of the cache is always given by the amount of data that the cache can be stored. The space you use for the tag and for the valid bit is not counted when we talk about the size of the cache. So this is a 4 kilobyte cache. And is directly mapped because I can take the index and I can find exactly the position in the cache where I find the data. So given this address, I'll take the I reserve 2 bits for the offset because my block has a single word. I'll take the 10 next bits and I use that as an index to select one of the 1024 entries in the cache. When I get to that entry, I'll take the bits that I have stored as a tag. So there are 20 bits for tag because the address has 32 bits. I have used 2 for offset and 10 for the index. So there are 20 bits left. Those 20 bits are for the tag. So I'm going to take the 20 bits in the tag here, and I'll compare with the 20 bits in the tag in the access that the processor is making. And if those two numbers are the same, and the valid bit is 1, 2, then I will tell the processor that that's a hit. I have the data in the cache, and I'll take the data and I'll provide the data to the processor. So this is to illustrate with a different type of diagramming how the access happens to the cache. If either the tag did not match with the tag of the address given the processor, or the valid bit was not 1, then I will provide the processor an answer that says this is not a hit, this is a miss, I don't have the data into the cache. So before we change the map, I'm going to stop this recording here and we're going to start the second part to this lecture.